Welcome, everyone. Thank you very much for joining to this presentation. I will start sharing my screen. Um, and well, this webinar is part of MTech Best Practices Initiative. MTech is a company which have more than 20 years history of successfully developing complex hardware design. That experience includes the area of the RTL verification, which is why I am making this presentation. My name is Esmaya de Samo. I am telecommunication engineer. I have been working in verification for the last 40 years. The agenda for this presentation is as follows. First, we will cover what is UVM, its history, and its pros and cons. Next, we will discuss UVM implementation, what are not based on SystemVerilog, and finally, we will dive deeper into the key UVM concept and functional verification. Well, we'll start with some history here. Universal Verification Methodology, UVM, is a standard methodology used for the HDL verification process. It includes ASICs or FPGAs. And also, it is a set of libraries in SystemVerilog. Acelera is a non-profit organization that aims to define standards for the electronic design automation and integrated circuit industry. Acelera is dedicated to develop a standard that improves the efficiency and quality of the hardware design and verification process. UVM is a standard to the HDL verification, and it continues to be developed by Acelera System Initiative. Acelera is a standard organization that supports a mix of user and vendor standards as well as develop the open interfaces. Acelera was founded in 2000 as a merge of two previous organizations, SystemVerilog International and VHDL International, and now is a leader organization in the IP industry. Acelera focuses on developing a standard that enhances the efficiency and quality of hardware design and verification process. The standards developed by Acelera are widely used in the semiconductor industry, as well in other industries, where hardware design and verification are critical, such as aerospace or defense. Some of the most well-known standards developed by Acelera are SystemC, a standard for hardware and software system modeling and simulation, SystemRDL, language to describe registers, UVM, of course, and IPXICT, which is a standard for description of management of intellectual property in complex systems. UVM is like a merge of previous efforts made by different big vendors in the industry. For here we have, for example, Cadence, which with the BA advisor developed in E. This is close to the 2000. They try or make they a first try to make a standard for the verification. In the same way, we have Siemens, we developed the advanced verification methodology in 2006. And for example, Synopsys, which also convert the beta-based reuse verification methodology to a library for SystemVerilog and call it verification methodology manual. What I'm trying to say here is UVM is a child of different efforts from different vendors. And just a tip, the E language was created by Veracity, now part of Cadence, and it was the first hardware verification language in the market. As we can see, UVM for SystemVerilog is a library that continues to be updated. The last available version was released in August of the last year, and it can be downloaded for free from the Acelera website. There is several benefits to using UVM for verification. I will try to be clear here. I will give a list about this. Reusability. UVM promote a modular and reusable verification component, which can help to reduce development time and improve the verification quality. Standardization. UVM provides a standardized methodology for developing testbench, which can help ensure consistency and interoperability across different project teams. Sorry, I moved the slides. Sorry about it. I will do it right now. Here's about the slides about the history. Sorry for that, guys. Sorry. How is it? UVM is an Acelera product developed by Acelera, and Acelera is formed by different vendors. Here we can see it. Also, how I was talking about the UVM history, Acelera is the UVM is based in different efforts previously done. Here we have a picture about that. And finally, here we can see the different version of the UVM history. And we can see the last version is of the last year. Sorry, I will go fast because I missed to move the slides. And here we have the pros about using UVM. Sorry for that. We have reusability, scalability, and we also have automation. The way to do the things in UVM are very standardized, and that allows to create frameworks to the ramp up of the project in verification. We will retake this topic in the next slides. But all these things, the idea is to improve the productivity and reduce the cost of the verification. Basically, is that the why this effort is made for all these vendors. In cons, what we have here, but the first con is the step learning curve. UVM have a step learning curve and require a significant amount of time and effort to master. The standard itself is complex and includes a large number of concepts, classes, methods, and must be understood in order to use it effectively. In the same way, you can have an overhead of complexity. UVM can be an over-engineered for small designs or projects, leading to an unnecessary overhead and complexity. It can result in a longer development times, longer code bases, or high verification cost, which is not the idea. You have a limited flexibility because if you are using the UVM libraries, you are really tied to SystemVerilog, and probably you will not use another kind of simulation tools to run the simulations of the test bench. The debugging challenge increased a little bit using UVM because you are using an abstraction level higher that make some things really easy, like reuse code. But in the same moment, that includes an intrinsic non-determinism of the simulation. And that could be hard to debug in projects. If you are using this test bench in a really advanced way with randomization and all the features this SystemVerilog plus UVM I love you, that can impact in the performance of the simulation. Probably if you have a complex randomized constraints in your test bench, that will take more time in simulation to run, to resolve this randomization. It's worth noting, however, that many of these challenges can be mitigated through proper training, design and implementation practice. Additionally, the benefit of using a standardized methodology like UVM often outweigh the potential drawbacks, especially in large and more complex projects. Here we can see some of these cons in numbers. For example, today UVM have more than 300 classes and 1,000 methods and 200 macros. That is a lot of information to learn to start to use this library. The other problem with UVM today is you have always new ways to do the same because it's this kind of merge of methodology, and that can be confused also. And in the end, it is this part of the SystemVerilog is an object-oriented programming. What means you have all a tree of hierarchies, but probably you will be using only the last part of the tree, and is a smaller part of the library you are really using in a project. And that can be confused and hard to understand in the first step of using these tools. Let's see. What is a good thing about these things? SystemVerilog allows to constrain definition in a really clear and easy way. We will retake the randomization topics in this presentation, but that allows you to make a good effort of verification more fast if you do directed test. In the same way, the cover points and cover groups that you can define to recollect coverage is easier to create that using SystemVerilog. Which are the cons? Well, we say if you see the number of keywords in the language of SystemVerilog are so higher compared with C++ or Python. And the last cons I put here have a little disclaimer, because if you are using UVM with SystemVerilog, probably you will need to use a proprietary simulator. The idea is Verilator in some point will be support a full UVM SystemVerilog libraries. And you, with the introduction of the Acelera System C UVM, you can use Verilator and the UVM methodology for the testbench. The good thing of this is you can incorporate C++ or C code in a really easy way because System C is based in C. And also System C can be used for the model of the RTL. Now let's talk about a non-SystemVerilog implementation of the UVM. We already talked about the System C, but we have also another open source initiative. Especially we are working on PyUVM, MTech, and collaboration with the University of Buenos Aires. We have working on implementing testbench using PyUVM and Cocotb for RTL design. We have successfully tested in this integration, and this for plain RTL. That means we are not using any intellectual property of any vendor in that designs. PyUVM is a UVM methodology implemented in Python instead of SystemVerilog, and PyUVM uses Cocotb to interact with the simulator. You can use it with the typical property simulator like Questa or Siemens, or with, for example, we try also with Verilator. That is a good thing because you are independent of the simulator. Let's talk about it, verification trends. What is doing the market? These reports are from Siemens website, and you can search it. And it was done using 980 eligible participants for make these numbers. How we say, on average, the demand of the ASICs design engineers grow in 2.5%, but the verification engineers grow even more, in a 6.2% if you compare the extreme of the years. It is a good news for us, I suppose. And I think it is also related with the increase of the complexity of the design and chips the industry is doing right now. In the same way, if we make the same numbers, but now in the FPGA area, we can see also the design engineers increased by 18% between 2012 and 2022. And the demand for the FPGA engineer increased in 38%. This is worth noting that during the period 2007 and 2040, the ASIC market went through similar growth demand related to verification engineers to address growing ASIC verification complexity. Now here we can see about what is used in the market to make this verification. We can see the majority trend is the use of verification tools and the implementation of the UVM in SystemVerilog for the ASIC industry. This combination of UVM SystemVerilog plus some property simulator is the more used way to make the verification. And also happened with the FPGA world, for say something. But here we can see a little trend to use more open source or not using verification at all. This is related with the nature of the FPGA design when you can reconfigure or change your design between you are developing it. The principal reason for this difference is basically the nature of both designs. Sorry for that. Here we can see the numbers for the what I'm talking about. Let's start with a little bit with what is important for us. Here the UVM architecture. It is a typical architecture you can find in this kind of testbench. You have agent, scoreboards, configuration classes. The agents are responsible to driving and monitoring the DUT signals. The scoreboarding the agent have another big important task, which is translate the signal to SEC items. That means you are here is the first abstraction level of the testbench. This agent will produce this SEC item from monitoring and will inject the signal based in the SEC item we will receive. The scoreboard will be connected over this component and will take some SEC items to make prediction about other ones, and finally will make the comparison between the predictions and with other agent monitoring in the DUT. DUT is device under test. The scoreboard have the responsibility to detect the problems in the design. And last, we have the configuration classes. The configuration classes are important because allow you to change the behavior of the components, and you can use it in ways in testbench when you have different environments. We see this next. The last component you can see here is the coverage collection component. The idea here is which gather functional coverage data. Here is a component, but in the real life, you can have the coverage collection distributed in different places of your testbench. Could be in interfaces or even in another places. Here we can see the UVM class hierarchy. We can see all the components and all the classes are child of UVM object. But you have two big families here. For one side, you have the components. Testbench element was lifetime extend through the simulation, and transaction, which are usually created and destroyed during the simulation. Typically, SEC items produced by the agents in the component, in the testbench. And here we finally have a UVM architecture which is reusing code. What that means? Here you have two environments. The idea is you can have this environment from block level simulation for some part of the DUT, and you reuse this environment in a bigger environment, and through the configuration class, you change the behavior of the agent. For example, you make some of that agent passive. In that way, is why the most strong quality of a feature of UVM is reuse the code in the testbench. This follow, if you are using this kind of architecture, you can use something known as UVM harness methodology, which that allows you to have only one testbench for all kinds of simulation, block level, cluster, or full chip simulation. It is really a powerful way to do the verification. Key concept in UVM. Here's a list of the things we think are the more important concept of UVM. We will follow it, but we'll do some in only one of these this concept. It's important to say here are not SystemVerilog key concept or SystemVerilog key parts of the standard. How we say we will have something object, and everything will be a child from this base class. Will we have components? We'll do different roles inside the testbench. We have the TLM transaction, which is the way the UVM have to propagate this transaction through all the testbench. UVM also use a lot of macros that allow you to have some kind of relationship with the factory. The factory is a big concept in UVM because it's which allow you to have more flexibility using the same code for different tests. You have the event pools. The event is a property of the SystemVerilog, but UVM take this event and introduce some own possibilities to use it. Another concept really important in UVM are the phases. The simulation is implemented in different phases, which allow you to, for example, jump between phases, really extreme use of it. And that allow you to, in an easy way, make a reset on the fly simulation. Transaction, we are already talking about this, probably will be a SEC item, and the component in charge to make this abstraction is the agent. The sequences are the way you can handle the stimulus through the driver and finally through the duty. But you also need to orchestrate this stimulus through different agents, through different stimulus to the duty. And for that, you can use virtual sequences. You also have callbacks. The callbacks is almost same with another language. Is a part of code will be triggered from some events or something specifically in the time sequence. Coverage, how we say, all the time you can be collecting functional coverage through cover point or cover groups. to, in the end of the regression, when you run many times your test, you can know if you are missing something. The configuration database, allow you to catch up different handlers from different parts of the test bench in a really easy way. It's like you can register something here and you can catch up that cycling in another place of the test bench. The factory is the way UVM can know which class exists inside the test bench and override this. And that is a really powerful and dangerous way to change the behavior of the test bench. It's really hard to debugging when you have problems with the factory registration. Could be a problem. Layering. We'll be talking about this next, but the layering is a component will be over the Asian, and the idea is you can elevate even more the abstraction level of your SEC items. And the register model, which is an example of the layering. Will we see this? Well, the first thing I want to talk is scoreboarding. How I say, scoreboarding have the work to first make the prediction. And that could be really hard, especially in our kind of project when we are doing a lot of this digital signal processing. You have filters, you have correlators. Make the prediction in SystemVerilog could be difficult, but SystemVerilog include DPI calls and system calls. In that way, you can integrate predictors in other languages. For example, MATLAB, Python, or C, or whatever you want to use it. That is really good because it makes easier the integration with the algorithm in your project. How we talk it here, zooming about layering, how say before, the layer are components which are connected through agent or another layer, for this example. And there is a problem which in their nature already have layers. For example, the telecommunication protocols. An example of this can be PCI, Ethernet, whatever thing where you can think in layers is an example way to have this abstraction in your test bench is using exactly layering. Which is the most important thing here? The layering will have two works. Translate the lower abstraction SEC item to higher abstraction SEC item, and exactly the opposite. Take the higher abstraction SEC item and translate this to lower. Is really useful not only for this kind of natural way to. Also, if you have designs when the interfaces to the UT are not 100% defined, you can put layering to elevate the abstraction of the test bench and encapsulate the changes related with the signal to the DUT. An example of using layering is the register abstraction layer, which is widely used example of layering, which raises the abstraction level of the UET register access. The idea here is you can forget if you are doing an AXI4 full or SPI or whatever. You will only drive in write or read transaction to the DUT, and doesn't matter through which interface or which nature of the interface you are using. Even you can handle multiple interfaces from the same register abstraction level through maps, That is really nice to do because you can forget about the signal level of this. There is several tools that with a simple register description can generate both the RTL and the corresponding UVM classes for the verification. An example of the open source of this is RDL, or maybe you can know the register assistant from Cuesta. Reuse code. We say one of the most important features of the UVM is you can reuse code. But this scale in a different way when we go deeper inside this. The way to do the things in UVM can be so structured that you can create frameworks. These frameworks with a few description or light description of the testbench will create a lot of the files and the classes you will need and you will use. For example, you can find the Siemens UVM framework from them free in the web. Also, you can adapt and create your own framework if you are an experienced user of UVM. In our case, we have a UVM code generator, which is using PyYAML and Jinja. And today we have an agent generator, an environment generator, and a layering generator. In our experience, the most used was the layering generator for the nature of some project we already have. That allows us to increase a lot the performance of the verification team. It is not exactly UVM, but it's something I want to discuss here. It's about how you create the stimulus to the design. You have the traditional or old way, which is with directed test, and you will create this directed sequence to stimulate the duty, and you will have probably a test for each of these golden path. The problem of that is take more time, basically, to coverage all the golden paths which are important or which are you need. One way to make this faster is using random inputs. The idea here is you're randomizing your input and send that to the DT, and you've left the golden path emerge from the regressions in a natural way. One question about this could be, well, what happens if I need to replicate a golden path or a sequence stimulus from the real lab because something is not working in some place? Well, SystemVerilog have a really powerful constraints options, and that is the way you can use your random test or test bench to emulate a directed test in the old way. The other question can be emerged from here is, well, okay, will you use random stimulus? When ends? When the verification effort ends? Well, the answer for that is you need to recollect coverage. You have two ways to do this. Or you have to do this in two ways: functional coverage and code coverage. Any feature of the design has to be related to any cover group or cover point to be sure all the feature is tested. And the code coverage will allow you to know if some part of the RTL you are testing are not stimulated. In both, the problem could be the stimulus. Maybe your input are not randomly in the efficient way, or in the code coverage problem, you can have some dead code inside RTL or states which never can be achieved, for example. For the nature of this problem, there is an increasing number of discussion about use AI for stimulus generation and meant to maximize the verification coverage while minimizing the number of the simulation needs. And on touch this line, the research is currently being explored. And finally, I want to talk about something out the UVM, which is another way to do verification, which is the formal verification. The formal verification, the input signal are assumed to have some kind of nurture, and the rest of the design is subject to some rules. The solver will cover all the possible options respecting the assumptions, and will report if there is any state that doesn't comply with the defined rules. If you see these two slides that put here, in a typical simulation, you are going through the states of the design in a golden path, even if that golden path comes from a directed test or a random test. In the formal, you don't have this golden path. You are trying and recovering and search in all the state space. The good thing is you will have code coverage 100% the first day, which is the problem. If your state space is too big, probably your simulation will never end or will crash before it can end. That is not good. Probably you need to start to break the design in smaller pieces to do this, or put some block boxes in some places to not include that spaces, that state spaces to your full design simulation. The way to declare these assumptions and these rules is using SystemVerilog assertions. The good thing is that SystemVerilog assertion can be also used in functional simulation. Not only using the typical UVM scoreboarding, if you are also using assertions, you can have almost the good thing of both together. Well, I'm good with time. I'm happy about that. This is what I think to say today. I don't know if it is any question or see here. One of the questions is about how to use these inputs when you have bad coverage. Okay, the question is if you have any example about problems in coverage will require change the stimulus. An example I have is for the last 2 weeks, I think, I was working with some colleagues. Some DSP process take maximum values. If you put a plain distribution, you will have always big values in the output of the maximum in a window of samples. And the way that requires to change the inputs. You can change the input distribution to have a better or more good distribution of the maximum of these samples inside a window. It's a typical problem you will find with coverage. That is the kind of thing that you can find using this randomization and coverage driver verification. And that is a typical problem. Well, thank you for your attention. I hope you found the talk interesting. Okay, I have some question here. Sorry, a moment. How the coverage in a system is measured? You have two ways. The code coverage is provided by your simulator tools. Basically, for example, you have the toggle coverage, code coverage, which is if the signal go to 0 and the 0 to 1 and the 1 to 0 in a simulation. That kind of coverage will give to you by your simulator. And the functional coverage, which is related to cover groups and cover groups, are component you can include in your test bench. What will be doing this kind of histogram about the signal or fields or whatever you are trying to recollect. You will run a big regression with a lot of kind of tests, and in the end, you will merge these coverage databases from the different simulations, and that is your status of your verification coverage. And then you can see if there is a signal will never change, or there is a register will never take a value higher than some parameters. That is the way you can collect the coverage and you can handle this. I don't know if there is. Okay. In the end, yeah, it's how you know you really finish. It's a really hard question to answer in the real life. The verification in the end is a risky handler task. In some point you have to finish. But the more important thing here is have a good specification. If you have a good specification, what the design have to do, there you will have a list of features. All the features have to have at least one coverage, cover point or cover group to be sure you are testing all the features of the design. And also you be sure if you are recovering or taking all the code of the RTL in your simulation stimulated. Basically, the only way to be 100% sure you are covering everything is go back to the basis. Review the code coverage and see you are not missing anything there. And review the specification and see you are not missing anything in the features. Yeah, of course. There is a question about which are the basic step for create an internal simulation of UVM. The first thing you have to define is which simulator you will use, because that requires a lot of scripting work about making work your design, your test bench with that simulator. After you have this, after you can run a simulation, you can start to thinking about the test bench itself. The first thing I think you have to do after you have the tools working is think about it. What kind of architecture of UVM you want to use? If it's a really small design, maybe you can use only one environment with your agents and with your scoreboarding only on one place. But if it's a really complex design, which is usually our case, probably you have to think in how you want to break this design in subsets or sub-environments. What kind of things you want to be verified in this block level or sub-environment level, and what kind of things have to be verified in a high level. My recommendation is start to think this and draw and see the boxes, if that has sense. That is in an architectural way if you want to think about it. Probably that in that place you also are defining the verification test plan, and probably you can do that together. Um, in a second way, the first thing you need are the agents, because if you don't have the agent, you cannot stimulate or monitoring the signals. That is a big problem. And the agent today, for example, for some protocols, you can use buy these agents with license to some of the vendors, or you can develop your own agents. It is a really delicate point because you have to trust in the agents to be sure the problems are in other place. If you have doubts about your agent is good enough, could be hard, but but you need an agent in the end of the day. At that point, you have your architecture, you have your agent, you have your tools working. You can start to develop the test bench itself. That depends a lot of the nature of the project. In some project, we are an external verification work, and that way you can think about the design like a black box and only see if in some points the design don't do whatever you want. If you are working high behind with the design team and you are involved in the development process, probably your test bench will grow up with the design, and that will be affect in the way you do the verification. Probably you will finally using a gray box methodology. And in the end, you have to run a lot of regression, and in the end, you have to be sure about the coverage. You need to run a lot of regression, see if something not correctly stimulated, see if something never stimulated, or is dead code, or the RTL have some problem to recover, to go to all these states possible. And then your work finish. That are the steps of the flow. Note, I never think about bugs, but in the middle of all these things, you will find bugs in your test bench or in the design. And it's also important to have a clear flow to report this and don't miss it. Because a typical thing what happens is you fix your test bench to pass even the bug, and if you don't have a good reporting process, you will forget that bug was there. That is a problem because it's not the way to do the things. I don't know. I know it was clear enough, but I think that is the steps. You can write an email if you want an answer with more clear way. If someone is looking to start a career in functional verification and they keep running into terms like SBI, functional coverage, UVM, they avoid feeling overwhelmed, and that's when learn this material. What learning path would you recommend? First, to start, I will start again. I am a person who would like go to the basis. Probably I will recommend go to Verification Academy website, which is a Siemens initiative. Really good material out there. You can have something like the codebook, which is the skeleton of the different components of the UVM based test bench. You can go also to the UVM standard. The UVM standard have a UVM user manual, which is really good to understand which is the idea to make the verification. And in the end, there is some books like Introduction to SystemVerilog for verification, which allow you to put all these concepts in a line, because there is something it's easy to be confused about which is SystemVerilog and which is UVM. I think with those three sources are the more important, or from my point of view, was the most important to try to understand this world. Okay, do you have a real example of coverage analysis that forces you to change the randomization of the stimulus? How we say, a typical problem is when you are trying to use DSP and you have some kind of saturation process or maximum, or the filtering, which if the uniform distribution is not the best option. The way to find that problem is reviewing the coverage. And the way to resolve that problem is using constraint in the randomization of the inputs. And I don't know, how long is the average development time of a test bench? Well, depends. And that will depend of the kind of project you are. Probably if you are in working shaft modification and the RTL go to your hands, almost finished or finished, the process will be really short, because you only have to develop the test bench and the test cases and follow the verification test plan. And will be depend the complex of the scoreboarding will take to create. But if the RTL is end, probably you already have the golden models to make the prediction. And I don't know, maybe months, weeks is a good number. But if you are working, giving support to the design team in the moment they are defining and implementing the design, the verification effort will take the same the design effort and little more, because you will change in your test bench. In the middle, the design is implementing his design, his specification, and even in the moment if the RTL is finished, you still need time to run the regression and analyze the coverage. The verification never can end before the design. That is the hard constraint of the timing of the verification effort. What is the key difference between using UVM for FPGA design or for an ASIC design? It is the last question. You have the nature is really different here, because in FPGA design, probably some things you are less strict with some kind of things. For example, is not usually to run a post-plus and write root simulation, for example. In the ASIC world, you need to be more strict with the timings and how the signals are propagated inside the design. And probably you will using more assertions than in the FPGA world. And the tools we are using probably will be different, and you can run your test bench with the physical models of the design and not only with the functional model of the design like is usually done in FPGA. That is, from my point of view, the big difference. You need to be more, you are thinking the problem in a different way. Because in FPGA, in the ASIC, you have to be 100% sure about all the condition of the propagation. And a lot of that problem is translated to the synthesized tools in the FPGA design world. Well, this was the last question. Thank you for your attention. I hope you found the talk interesting, and don't hesitate to contact us for any question you might have. A good day. Bye bye.